You see planets as silent, solid spheres, bright dots of color, distant orbs, floating in the blackness of space. But what you cannot see is the most critical layer that defines every single one of them, their atmosphere. This invisible blanket of gas is not just a passive wrapper around a planet. It is an active, powerful architect that writes the story of a world's climate, its temperature, its geology, and even its chance to hold life. For billions of years, atmospheres have been the quiet rulers of our solar system, and every planetary system beyond turning rocky cores into habitable havens, toxic infernos, frozen deserts, or swirling storm factories. To understand the universe is to understand atmospheres, how they form, how they change, and how they hold the power to make or break a planet's fate. Let us journey across the solar system and into deep space to uncover the hidden rules of planetary atmospheres and see why this thin layer of gas is the single most important factor in a world's identity. Long before Earth had oceans, trees, or animals, it was a molten rock bombarded by asteroids and comets, with no air to speak of. The first atmospheres of rocky planets like Earth, Venus, and Mars came from within volcanoes, erupting, spewing carbon dioxide, water vapor, nitrogen, and other gases into the void. Early in solar system history, these three terrestrial worlds started with similar building blocks, but their atmospheres took wildly different paths, leading to the vastly different worlds we see today. Earth's atmosphere became a delicate, life-sustaining mix. Venus's turned into a crushing, scorching hell. Mars's faded away, leaving a cold, barren rock. The difference was not luck. It was physics, chemistry, and the delicate balance of a planet's size, distance from the sun, and magnetic field, all factors that control how an atmosphere forms, evolves, and survives. Let us start with the one we know best, Earth. Our atmosphere is a thin, fragile shell, just 100 kilometers thick, from the surface to the edge of space, thinner than the skin of an apple, compared to the planet's size. Yet this tiny layer does everything. It traps just enough heat from the sun to keep our planet at a perfect 15 degrees Celsius on average, allowing liquid water to exist everywhere. Liquid water is the foundation of life as we know it, and Earth's atmosphere is the reason water does not boil away into space or freeze solid into ice. Our air is 78% nitrogen, 21% oxygen, and trace amounts of carbon dioxide, argon, and water vapor, an exact mix that plants, animals, and humans need to breathe. The ozone layer, high in our stratosphere, blocks harmful ultraviolet radiation from the sun, protecting all life on the surface from deadly damage. Our atmosphere also drives weather systems, wind, rain, snow, clouds, and storms that recycle water-shaped landscapes and keep our planet's systems in balance. Without this atmosphere, Earth would be an airless rock, with temperatures swinging from hundreds of degrees above freezing during the day to hundreds below at night, just like the moon. We often take our air for granted, but it is a cosmic miracle, a perfect balance that took 4.5 billion years to create. Now look to our nearest neighbor, Venus, often called Earth's twin, because it is almost the same size and mass, and formed from the same solar material. But Venus' atmosphere tells a story of disaster, a cautionary tale of what happens when an atmosphere spirals out of control. Venus' atmosphere is almost entirely carbon dioxide, with thick clouds of sulfuric acid that cover the entire planet. The pressure at Venus's surface is 92 times that of Earth, equal to the pressure 1 kilometer deep in Earth oceans. The temperature is a blistering 462 degrees Celsius, hot enough to melt lead and turn any water into steam instantly. This is the runaway greenhouse effect. Carbon dioxide traps every bit of the sun's heat, with no way for it to escape. Early Venus may have had oceans and a mild climate, just like early Earth. But as the sun grew brighter, Venus' oceans evaporated, adding more water vapor to the atmosphere, a potent greenhouse gas. The heat broke apart, water molecules and hydrogen escaped into space, leaving oxygen to bond with carbon, creating more carbon dioxide. The cycle fed on itself, turning a potentially habitable world into the hottest planet in the solar system. Venus teaches us a critical lesson: an atmosphere is not stable forever. Small changes can snowball into planetary catastrophe, and the line between life and death is razor thin. Next is Mars, the red planet, a world that lost its atmosphere and lost its chance to be a living world. Billions of years ago, Mars had a thick atmosphere, liquid water, rivers, lakes, and maybe even oceans. NASA's rovers, Curiosity, Perseverance, have found ancient riverbeds, mineral deposits formed in water and clay layers that prove Mars was once warm and wet. So what happened? Mars is smaller than Earth, with a weaker gravity that cannot hold onto light gases as easily. Worse, Mars's core cooled down and its magnetic field disappeared. Without a magnetic field, the solar wind, an endless stream of charged particles from the sun, stripped Mars's atmosphere away, molecule by molecule, over billions of years. Today, Mars's atmosphere is less than 1% as thick as Earth's, made mostly of carbon dioxide. The thin air cannot trap heat, so Mars' average temperature is minus 63 degrees Celsius. Liquid water cannot exist on the surface for long. It either freezes or boils away into the thin atmosphere. Mars is a frozen desert, a ghost of what it once was, a perfect example of how losing an atmosphere means losing a planet's vitality. NASA's MAVEN mission has spent years studying Mars's atmospheric escape, giving us a clear picture of how a world dies when its protective blanket is torn away. Beyond the rocky terrestrial planets, the gas giants Jupiter, Saturn, Uranus, Neptune have atmospheres that are the planet itself. These worlds have no solid surface. Their atmospheres are thousands of kilometers thick, made mostly of hydrogen and helium, the same gases that make up the Sunday. Jupiter's atmosphere is a violent masterpiece of storms and clouds. The Great Red Spot, a storm bigger than Earth, has raged for over 300 years, powered by heat from the planet's core and rapid rotation. Saturn's atmosphere has faint, beautiful bands, and the famous hexagonal storm at its north pole, a geometric wonder created by atmospheric winds. Uranus and Neptune, the ice giants, have atmospheres rich in methane, which gives them their blue color, and supersonic winds that race across their surfaces at 2,000 kilometers per hour. These giant atmospheres are not just for show. They shape the entire planet's behavior, from its internal heat to its magnetic fields, and they hold clues to how our solar system formed from the solar nebula. Even the moons of these giants have incredible atmospheres. Titan, Saturn's largest moon, has a thick nitrogen atmosphere with liquid methane lakes and rain, making it the only other world in the solar system with stable liquid on its surface. Titan's atmosphere is so dense that its surface pressure is higher than Earth's, and it is a prime target for astrobiologists searching for the building blocks of life. Atmospheres also hold the key to finding life beyond our solar system. For the past 30 years, astronomers have discovered thousands of exoplanets, planets, orbiting other stars, and the James Webb Space Telescope is now studying their atmospheres for signs of life, called biosignatures. When an exoplanet passes in front of its star, some starlight filters through the planet's atmosphere, and telescopes can detect which gases are present. Oxygen, methane, ozone, and other gases that cannot exist together without life are the signs we look for. The James Webb has already detected carbon dioxide, water vapor, and methane in exoplanet atmospheres, bringing us closer than ever to finding a world with a life-sustaining atmosphere just like Earth. Every exoplanet atmosphere we study teaches us more about how common habitable worlds are and how unique or how ordinary Earth's atmosphere really is. The rules of atmospheres are universal, applying to every planet in every corner of the cosmos. A planet's size determines its gravity, which controls how much atmosphere it can hold. Its distance from its star determines how much heat it receives and whether the greenhouse effect keeps it warm or cooks it alive. Its magnetic field protects the atmosphere from the solar wind, keeping it from being stripped away. Its geology, volcanoes, plate tectonics, recycles gases, and keeps the atmosphere balanced. All these factors work together to create an atmosphere that either supports life, destroys it, or leaves a world frozen and dead. We are only beginning to unlock all the secrets of planetary atmospheres, but every discovery brings us closer to understanding our place in the universe. Earth's atmosphere is a precious gift, a delicate balance that we must protect. As we study other worlds and see the consequences of a broken or lost atmosphere, we learn how fragile our own air is. Human activity is changing Earth's atmosphere, adding more carbon dioxide, and warming the planet, a reminder that atmospheres are not permanent. The lessons from Venus, Mars, and every other planet in the solar system are clear. An atmosphere is a planet's most vital resource, and its fate is tied directly to the air that surrounds it. The next time you take a breath, remember that you are breathing the same atmosphere that has shaped Earth for billions of years, the same force that rules every world in the cosmos. The invisible architect is all around us, and its story is the greatest story in space exploration. Please like, comment, share, and subscribe to the channel.